So today I'm gonna be talking about a project that I did a couple of years back, where I built a simplest neural network you can imagine using VEX. And let me just introduce myself. My name is Ivan. You can find me on Instagram by my less appropriate name, Sex with a Whale Incorporated. You can also find me on LinkedIn. I've been doing some visual effects work. I've been working on projection mapping. But recently I found myself more into motion design and commercials. So here's just my show reel. I'm not going to be talking about any beautiful stuff or how to create a picture, how to render things, and this talk would be more technical. So why did I do this neural network inside Houdini using VEX? Mostly to learn, because I'm going to be honest with you, the setup that I'm going to show you today, it's not really practically usable. You wouldn't work with it in production. For any way, but the reason for me was to understand how those magic things called neural network work. And yeah, it was the start of pandemic. I had some free time. There was things like StyleGAN 2 by NVIDIA showing beautiful pictures. I think that back in the days, there was also a tool from Side Effects where they trained a neural network that would allow you to draw ridges and valleys on a picture and then get a height field out of it. So I was like, how this all works, what's underneath it. And I didn't come up with any of maths, obviously, here. I used a couple books. One of them is Make Your Own Neural Network. It's about how you can create one using Python. And then there is The Nature of Code by Daniel Shipman, who also has a beautiful YouTube channel where he dives into exploring different algorithms and how you can build them using JavaScript or P5. And sometimes I watch it and I'm like, oh, can I do this same thing in Houdini? It's a nice exercise. So let's dive inside. What's an artificial neural network? Back in the days, I think it was the middle of 20th century, people were really fascinated by our brains, and they thought, well, how we can transform this into a computer program. And this is not an exact representation of a human neuron. It's what Gemini thinks neuron can look like in the style of Ernst Haeckel. So a neuron is this processing unit that has a lot of dendrites, which are input connections to the neuron. And then there is one output connection, which is axon. An axon connects to other neurons through a synapse. This connection is called synapse. And this is how our brain is wired, just from one neuron to another, highlighting electrical signals running through it. And this is a schematic view of how an artificial network works as well. It's not how I build it inside VOPs. It's just everybody here, I guess, is familiar with VOPs, more or less. So you have a bunch of inputs in the input layer, then there are some hidden layers in between, and then there's an output layer. So you can imagine it on the left side where you have inputs, you get the tokens from your word prompt, and then on the output you have a bunch of pixels, which is your image in the end. If we're talking about something like Midjourney. There are different ways of how you can train a neural network. There is a supervised learning. This is exactly, so you have a prompt and you have a result for this prompt, so a description and then an image, and then you train your neural network to understand the correlation between those two. So you have a question and you have an answer, and then you try to mimic answers for other questions that you didn't have in your original data set. Then there is unsupervised learning, and the talk on principal component analysis from yesterday was a good example of unsupervised learning, where you don't have a specific answer, but you're like, okay, I have these things, and I want to kind of train and make my neural network understand what are the underlying principles of it and how I can get results in between. And then there is reinforcement learning, which is, if you can imagine an agent moving through a labyrinth, and you're saying, okay, if you are getting closer to the finish line, you're getting more points, and then you run this agent, I don't know, several thousand times, and it understands that it gets reinforced for a good behavior, and then when it leads to some bad place, it doesn't get any points. So the neural network kind of learns. And today we're gonna be talking about supervised learning in this talk. Let's see what the smallest part of the neural network is, and it's called perceptron, or perceptron, and it's a built-in block. It's basically a fancy way to name an artificial neuron. Again, just a schematic representation. You have this processing unit, and then you have an arbitrary number of inputs. You feed the inputs, and you get some kind of output through the magic that happens inside. And this magic is actually pretty simple. I mean, there are a bunch of formulas, but it's easily boiled down to school maths. So every input that you have has a weight. This weight is something that you adjust while you train your neural network. So you take all your inputs, multiply by respective weights, and you sum it all up. And then you have some number, and it might be really big, it might be really small, it might be negative, and you want a way to kind of work with it later. And the more understandable format is something in the range of 0 to 1, for example. It's really easy to work with numbers from 0 to 1. So there is an activation function that processes this weighted sum that you just got. It can be really anything, like there's a bunch of different ones, but we're gonna be taking a look at two of those. One of them is a sign function, which basically just tells you if you have a positive number or a negative number. And another one is slightly more interesting. It's called a sigmoid function, and it's 1 divided by 1 plus e in the power of x. And the nice thing about this one is that when you have a really large weighted sum, like really large x, your function tends to go to 1. And if you, to 0. And if you have a really small x, it goes to 1. So again, you get a nice range from 0 to 1. You get like an S-shaped function here. So this is basically what it does. It's not that complex. I mean, a couple of nodes, honestly. And this is what's called a feed-forward algorithm. So you're feeding your information from the input to the output. In case of more neurons in a larger network, it's going to be several steps. But in our case, with simple perceptron, it's just those basic math function. Once you get that output, you want to know how it relates to your target output. So you have a marked data set. You're like, OK, when I feed this input, I should get this target output. And you want to find an error, like how far away you are from where you want it to be. Once you get that error, you can then propagate it back and understand how you should adjust those weights on your connections so that you relate more to the proper final result. And then you have a concept of learning rate, because you don't want to get straight to the answer. because in this way, you're going to be adjusting your neural network for each specific input. And this is not what you wanted to do. You want it to be universal, generic to all different input results, not only give you the right answer for this particular right input. And then you repeat it over your data set, and your neural network learns what you want to get. Let's take a look at a simple example. We have here just two sets of points on a 2D grid. So our input data would be just x and y coordinates. And this can be different things, like the stuff that Moritz showed us in the previous example. He had a 3-dimensional space, but this might be just like, I don't know, cats and dogs. And you have their weight on one axis and their body length on the other axis. And you're like, OK, these are two sets. They intersect somewhere. And the way that we would name them is just class 0 and class 1. So again, just an attribute to distinguish between those two. And this is how the perceptron would look like. So again, we have 3 inputs. One of them is x coordinate, the other is y, and the third one is something called bias. It's just there for the case where we would have both x and y 0. We don't want to get 0 out of our perceptron. We want it to be at least some number. So this is why we have this. It's constant. It's always 1. And we're still going to be adjusting the weight on that connection as well. And then, yeah, we have an output, which would be -1 to 1. Or 1, because we're going to be using the sign function for the activation. And we're just going to transform it into 0 and 1 for the class, but it doesn't matter. Here's how it looks in the Houdini. So I'm going to be operating on that 2 clusters of points. And you see here, I have an attribute weights, which is just 3 float numbers. I randomize them between 0 and 1, and those are detail attributes. So they will stay on the geometry for the whole process of learning. And they're just going to be adjusted from step to step. And then every frame, I'm leaving only 1 point of the data set of, I think, 1,000 points. And this is just for 1 step. So each step, we have a different random point from the data set. Here's how it looks inside. It's just like everything is done in 1 wrangle almost. And it looks large, but because I have half of it is just comments. And the first part you can see is just me getting the data. So I'm getting the positions. I'm assigning the bias to be always 1. I'm taking those weights, applying the learning rate from a slider down there. And then we have a feed-forward algorithm, which, again, just 3 numbers multiplied by the respective weights, sum it all together, then check if this is plus or minus, positive number or negative. And then we check if that correlates with the output that we have. So is this a blue point or a purple point? And then we do the adjusting of the weights based on this error. So if the output is good, we don't do anything because it would be just 0 for adjusting the weights. But if it's different, if we have some error, then we're going to be adjusting those points. And I think I ran it about 1,000 iterations or something. And you can see, so those are our original points there. And then there is a bunch of points randomly scattered on the plane, which I'm coloring yellow or green. And those are predictions. So our network learns from the data set to predict if a random point on a surface would be more like a purple one or a blue one. And if you do some school math again, you can boil our weighted sum function to the line equation y equals ax plus b, which kind of leads us to an understanding that we're just approximating a separation line of those 2 sets of points. And this is actually a problem because To approximate a more interesting function, a more interesting task, we would need a multi-layer perceptron. And some smart people, they were like trying to understand why it is, and they came to a conclusion that perceptron can only solve a linearly separable problem. And what it is basically what we saw before, but here's a more clear example. So on the left here, we have a linearly separable problem. You can easily, with your eyes, draw a line which would separate those. But on the right, you kind of need a more interesting shape, I guess. But I don't trust scientists. I love to check stuff. So I ran my algorithm on those. And you see on the left, it kind of like almost instantly knows what to do. And on the right, it just like, I don't know what the hell is happening. And it turns out that a really simple function like XOR, exclusive OR, is actually as linearly inseparable. You can see, so it's a function that only true when one of your input numbers is true. If both of your numbers are true, it's 0. If they both false, it's false. And yeah, so you can see you can't draw one line. You need at least two to separate this problem. That's why it's a good example to test our multi-layer perceptron. So we have here the same block, but it's copied 3 times, or 4 times actually. So 3 times in the hidden layer, and then 1 time in the output layer. And as input in this example, we're going to be using just 2 numbers, as they could be both 0 or 1s. And the bias, which always stays 1, like in the previous example. And in this case, you might think, OK, I need to do my calculations for each of those perceptrons. It might take me a while. But then there's a thing called matrix multiplication, which actually allows you to do it really easily. So you can take all of those perceptrons in one layer and actually do the maths of calculating the whole input thing. You just take an input matrix multiplied by a matrix of your weights, and then you get your output result. And then you have to run the activation function on them. But that basically really makes it easy for you, but only if you do it in Python or JavaScript or somewhere where you have two-dimensional matrices and also a way to work with them, like NumPy, for example, a library for Python. But we don't have it in Houdini. And actually, we don't have even a two-dimensional arrays. There is transformation metrics, but if you try to go further than 4x4, you would need to come up with something. That's why we're going to use another way to try and optimize this. So what I'm going to be doing is, right now, I'm going to try and implement this same format, like this structure of a neural network, but I'm using points and lines between those points as a geometric representation, as a structure. And I'm going to be running a point triangle on those points in one layer at the same time. And you know that wrangles, they're kind of multi-threaded, so they can run at the same time on multiple points, which is great for us. So the network on the right actually just built these 7 points with respective connections in between them. And on points, I have, I think, 2 main attributes. One of them is the value that we're going to be calculating, and another is error. And then they have groups for layers to distinguish between one another. And then the lines, because they're connections, they have a weight attribute that we're going to be adjusting later. This is our training data. It's just 4 points, because we can have only 4 combinations of 0s and 1s into numbers. And we're going to be just, again, deleting randomly 1 point every frame, and just going to iterate like 3,000 times, I think, around those 4 points, and hope that our neural network will train and understand it. Here's how it looks in the solver. It's a little more complex, and this time I'm using a sigmoid function as activation, but the steps are the same. So first, we're going to do a feed-forward algorithm. So we're going to first do the calculation of the weighted sum from input layer multiplied by respective weights, and then take a sum of it, and then apply an activation function. And then we're going to do the same thing, but we're going to take our output from the hidden layer and then propagate it onto an output layer. And we'll get a result this way. And then we're going to calculate our error. Remember, we can only get 0 or 1 as our output. So we're just going to see if we got it or not. And then we're going to propagate this error back on our hidden layer, because we want to know how much each of those inputs contributing to the error. And to do that, we're going to need to take a normalized weight for each of the errors. So imagine you have this weight at the top, which is like 0.9, and those two, they're just 0.1 combined together. So we understand that this neuron at the top actually brings more to the error. So we have to adjust weights respective to it a little more. And this is what we do here. Like, this is how you write it in maths, and then this is how I wrote it in code, but I actually, I couldn't make it work in how it should look in theory. And I didn't normalize the weights. I still multiply by respective weight each error, but it didn't work for me in the proper way. But the neural network actually learned this improper way. And if somebody can find a flaw here, I would be really pleased to know what it is, because I tried to do it back when I came up with this setup. I tried to do it when I was preparing this presentation. I couldn't find an error, but it's probably something with a minus somewhere. And then our last step is adjusting the weights on the connections. Now that we know all the respective errors to each of the neurons, we can calculate the error. And the formula is kind of the same, except since in previous example we used a sine function, it was really easy. But since here we are using a sigmoid function, which is again 1 divided by 1 plus e in the power of x, we actually want to know when we change our x, how much the function result changes. And for this, there is a thing in the math called derivative, and it just shows you, if you adjust x a little bit, how far your final function will be adjusted. So we use this derivative to adjust our weights based on the outputs and the errors that we have. Again, might look a little complicated, but we're just multiplying things here. And then we have this representation of how it works. It's a little counterintuitive, I guess, but you see those markings. So in the corners, we have those true or false, and everything in between is kind of, I don't know, I'm not sure, maybe. So 0.5, 0.7, it's hard to understand this in terms of when you're only working with 0 and 1. But you can see that around iteration 1500, somewhere in between, you start to see this blue line, red line that goes diagonally. So you distinguish between those false, so true and true that you have in left bottom and right top, and then false that you have at left top and right bottom. And actually, if you randomize weights differently, you might get a diagonal in another direction, because there is really no matter how you distinguish that based on our input data. Okay, and here's just a picture that I took this morning, because I thought, okay, we made it so far into presentation. I still have 15 slides. but you really deserve this moment of tranquility. But yeah, let's go further. This was really fun, and we made already 2 neural networks. They were really simple, but there is no use case for them whatsoever. So why we don't try something more difficult? And we're gonna try and build a neural network that's gonna be distinguishing handwritten digits. And this is the thing that you might noticed in the previous presentation. MNIST dataset is a set of 70,000 small images, 28 by 28 pixels, and it's used for training different neural networks and seeing how well your neural network behaves in this scenario. So we're going to use that and try to make something that sees these numbers and says, okay, this might be 7, this is 5. Here's actually the only place where I'm using Python is to load this data set into Houdini and convert it into points. So for each data point, I have a physical, or like, not really physical, but a point inside Houdini. So we have 70,000 points. Each of them has 2 attributes. One is an array attribute X, which is just color intensity of each pixel. So if you have a 28 by 28 pixel image, you have 784 pixels total. And then you have a Y array attribute, which tells you which of the digits it is. So all of those going to be 0 except for one of them. So if it's 0, only the first number would be 1. If it's, say, 5, only the 5th number would be 1. And then this is the same that you've seen before, but I just wrapped it inside an asset, which allows you to select arbitrary number of hidden layers and the number of neurons that you have in your hidden layers, input layer, output layer, but still just a bunch of points and a bunch of connections between them. And this is already a working example, but again, we're looking at the structure. We have 784 input neurons, which respectively correlate to those pixels in the images. And then I took 20 neurons in the hidden layer, and then we have 10 output neurons, which again just tell us which number it is. We're gonna be doing same thing as before. We're gonna initialize the weights on the connections randomly. There are smarter ways to do that, but I'm just taking an easy way here. Then we're gonna feed forward our data to the hidden layer and then to the output layer. We're gonna calculate the error, and we're gonna propagate this error back and see how we should adjust our weights. And we're gonna do this 100,000 steps. And this is how the network looks in Houdini. Top right, you can see I'm bringing in the data set and dividing it into a training data set and test data set, because as been mentioned before, you don't want to train your network, test your network on the same things that you've been training it, because it's going to be just giving you good results for your trained data, but not going to be generalized well. And then each frame, I'm leaving just one point in training. Left top, we have the structure, and then a little switch in case you want to do some training, and then take your previous training and continue on another data set, or just do more iterations. Then we are going just to apply this data to the input layer. So again, I'm just taking this X attribute that I have on my data set and distributing 784 numbers to different points, one on each point. Then the training asset, we're going to dive into it later. And then to test how our network performs, we again applied the data, same asset, just applying the test data on the input layer, and an asset that does a feed-forward algorithm that is a part of a training asset as well. what we do inside is, again, it's almost the same thing, only here I wrapped the feed-forward and back propagation algorithms into for each layers, for each loops, so that you can account for multiple layers, not just one hidden layer, even though in this example we're only using one. But technically it can be any number of layers. And then, again, same thing, weighted sum, activation function, calculating the error on the hidden layers through the normalized weighted sum, and weight adjustment. It's basically the same code that I've used before, even though the network seems to be a little more complicated. And then after 100,000 iterations, the training time for that was around 15 minutes. We get something that actually gives us pleasing results. I mean, it's not that good at the beginning, but closer to the end of iteration cycle, or training, I should say, it becomes a little more. It behaves differently for different numbers, so some of them are easier to distinguish than others. And for that, I actually calculated the accuracy of it. So it almost in 90% of the time, it does a good prediction. And you can also see how many errors it does for each of the digits there. But again, some of it is partially because our handwritings are really different, and I don't know who writes 5 like this. I mean, I can see that it's probably not a 6, but still, the data set is really diverse. So partially is because our neural network is really simple, but still, it is one, and it works, it learns. And it's really fast. And I actually tried an alternative structure, which I did actually last evening. I just took 40 neurons in the hidden layer instead of 20, and it actually increased the accuracy to 94%, which is a lot better. I actually tried 2 hidden layers as well, but that didn't lead to any good results. And this is a little video of me just trying, almost in real time, just drawing some numbers and seeing how well it behaves. Some numbers are really hard for the neural network, like 3, for example, or 2. It's just hard to get them, but it's fun to play with it and try to know, kind of like, can I just fool my network and start drawing one number and then add something to it and make it into another number? Will it understand 2? Finally does. Then kind of transform it into 8, but the network thought it's 6. So it's really fun to play, and this really helped me to understand how those neural networks work under the hood. I hope that my talk also helped you as well, just to get a little more knowledge on what happens there behind the curtains. But yeah, what I really want you to take away from this presentation is that Houdini is approximately 2, and love is 7. Thank you so much.
Thanks, Ivan. Are there any questions? Speechless. So.
Thank you very much for the presentation. You started by saying that at this stage you don't have any application for that in production. It was just a learning opportunity, but now that you've done it, do you see a way to push it forward and how you might use it in production?
Well, I feel like there is no really way. Like, you can still play with it. You can try different examples. You can even try more complex neural networks, like trying to build a convolutional neural network with just a different structure of the network. So this one was fully connected. Each neuron is connected to each one in the previous and next layer. And there are like more complicated ones. But really, if you want to do this, you better do this in Python. And even in Houdini's new tool set, because that way you'll be actually experimenting with the network itself and not with like how it works. So I don't think that this specific example, it's not optimized, like running through the VEX, all of this, it's not the best way to do it for sure.
Thank you.
Anybody else? No. Thanks, Ivan.
Thank you.